Lesson 7.8, Exponential Growth and Decay. Exponential growth and decay are represented by exponential functions. These are functions in which the variable is the exponent. These functions describe real-world growth and decay scenarios, such as population increases and decreases, plants growing, things being used up, bank interest, team eliminations, and many more real-world situations. In order to understand exponential growth and decay, we need to use the exponential function, and there are two forms of the exponential function. We have y is equal to a times b to the power of x, and a variation, y is equal to c times 1 plus r to the t. Exponential growth is an example of a geometric sequence. Now, we had discussed arithmetic sequences earlier. Unlike an arithmetic sequence, which involves adding and subtracting to get from one term to the next, a geometric sequence uses multiplication and division, and we represent any division as a multiplication by a fraction. All exponential growth functions have the basic shape of the graph shown here. The curve can be more or less pronounced, and we can flip the graph. So, for example, it could bend this way instead, but the shape will always be the same. Some real-world examples of exponential growth: bacteria colonies, population in an area, zombies. Okay, maybe that one's not so real-world, but zombies grow exponentially. The basic equation for exponential growth is y is equal to ab to the x. A is the starting value. This is the first term in the sequence. B is the base, and it has to be greater than 1. This is the growth factor, and that's the amount that is being multiplied by each time in the sequence. X is the exponent, and it represents the number of times B has been applied in the sequence. So, for example, if we're on the 5th term of the sequence, B has been applied 4 times. So it would be x would be 4. Okay, here's an example of an exponential function. We have the function of x is 2 to the x. In this case, a would equal 1, b is 2, and x is just x. Then the x-axis is known as the asymptote, because while it looks like this graph is touching the x-axis, an asymptote is a line that the graph never touches or crosses. But it gets extremely close to. Okay, and there should be arrows here. As you can see, this is going to continue to go up and up and up and up and up. So if we do some examples, when x is 0, we get 2 to the 0, so that's 1. When x is 1, we get 2 to the 1st, so that's 2. When x is 2, we get 2 squared, so it's 4. If x was 10, we'd have 2 to the 10th, which is 1024. So you can see it gets very large very quickly. And to show how we never actually approach or hit the x-axis, I'll go on the negative direction. If x is -1, I get 2 to the -1, which is 1/2. If x is -2, I get 2 to the -2, which is 1/4. If x is -10, I get 2 to the -10, which is 1/1024. And if we keep going bigger, let's say I use -150, I'll have 2 to the -150, and that would give me, well, quite honestly, a really large number. It's going to give me 1/2, 1.4 times 10 to the 45th. And if I did negative 600, I'll have 2 to the negative 600, which is going to give me 1 over. And see, my calculator won't even do that because it's such a large value down in the denominator. But you can see that we can never put in a number to where we'll actually hit that x-axis. There is no exponent that I raise 2 to that will give me a 0. This does not exist. And that's what creates the asymptote. We have variations on exponential growth. Sometimes it's not an increase of a factor of b. So for example, we're not multiplying by 2 every time, but rather by a percentage. And that gives us a different equation. Y is equal to c times 1 plus r to the t. Just to go over this, c is our starting point. So it's the first number in the sequence. R is our percent as a decimal. And t is the length of time that this has occurred in years. So some examples of this type of growth include compound interest in a bank account or on a loan, population, business growth. So when we have our compound interest formula, B is our balance. C was our starting point. Well, in this case, it's our initial deposit, known as the principal. R is our percent of interest, and T is still number of years. So if I deposit $3,000 in an account that pays 2.5% interest for 6 years, how much money will I have? So we're looking at the exponential growth. Now what I need to do is, first I need to turn that 2.5% into a decimal. So I move 2 places to the left. So that's going to be 0.025. So that's R. C is my initial deposit of $3,000, and T is 6 for 6 years. So when I plug that in, I'll have the balance is equal to 3,000 times 1 plus 0.025 to the 6th. We do what's inside the parentheses first, so that's 1.025 to the 6th. Next comes exponents. So I 1.025, I raise that to the power of 6. That'll give me 3,000 times 1.159693, etc. So I multiply that by 3,000. And my balance will be $3,479.08. So that's how compound interest works, and that is an exponential function. Now, exponential decay occurs when things are decreasing. This is the opposite of growth. Growth is increasing, decay is decreasing. This is when a population or sequence is declining at a constant rate. And we still use y equals ab to the x, but in a decay function, while a is still the starting value, b is between 0 and 1 instead of being greater than 1. This is the decay factor. So it's the amount being multiplied each time, and sometimes it's a division, but we do multiplication by a fraction. And x, again, is the exponent and is not equal to 0. So we can use this equation as well to represent decay that occurs at a regular percentage. Everything is the same, except instead of adding, we subtract. Okay, so here's some examples. A dish has 212 bacteria in it. The population of bacteria will grow by 80% every 2 days. How many bacteria will be present in 4 days, 8 days, or 11 days? So let's look at the formula that we need to use. We have a percentage increase, and that means we need to use y is equal to c times 1 plus r to the t. Now the t in this case is not years, it's every 2 days. So t is equal to 2 days. So that would be 1t. So 2t would be 4 days. 3t would be 6, etc. So when 2 is equal to t, that t equals 2, that's 4 days. When t equals 3, that's 6 days, etc. So in 4 days, we're going to set up our formula. C is our starting point, so that's 212 bacteria. I need to convert 80% to a decimal, so I move 2 places to the left. That's 0.8, so plus 0.8. And I want 4 days, so t will be 2 in this case. So I'm going to do 212 times 1.8 squared. So first I'll need to square the 1.8, and that's going to give me 3.24, and then I multiply that times 212, and in 4 days there will be 686.8, so approximately 687 bacteria, because we can't have a part of a bacteria. In 8 days, t will be 4, so I will set up the same equation, 1 plus 0.8, except this time to the 4th. So 212 times 1.8 to the 4th. So I need to do 1.8 to the 4th first. That gives me 10.4976. Multiply that by 212. And at this point in time, we'll have 225.5, so 226 bacteria, because again, we can't have part of a bacteria. Now here where t is 11 days, 11 divided by 2 is 5.5. So that's what t will equal, is 5.5. So I'll have 212 times 1.8 to the 5.5. So I'll raise 1.8 to the 5.5. And I get 25.35. So I'll do 212 times 25.35. It's actually 35121, etc. It goes on and on and on. And I multiply that by 212. And I get 5,374.5, so 5,375 bacteria will be in that dish within 11 days. Let's check another example. Oh, first, I'm sorry, does this represent growth or decay? Well, we started with 212 here. We end up with 5,000, so I would say that that was definite growth. Okay, here we have a baby brother with an ear infection, and the doctor said that there are probably 50 million bacteria in his left ear, and the penicillin they gave will kill 7% of the bacteria every 6 hours. So 1t is equal to 6 hours. Now, we want to know how many bacteria will be in our brother's ear in 1 day, 5 days, 1 week, or in 3 hours. Well, 1 day is equal to 24 hours. So t would be 4 there, because 24 divided by 6 is 4. And since we're killing the bacteria, that's us decreasing the bacteria. So in this instance, we need to use the 1 minus r formula. So I start with 50 million times 1 minus 0.07, 7% converted to a decimal, we move 2 places, and t is going to be 4. So I have 1 minus 0.07. That gives me 0.93. So I have 50 million times 0.93 to the 4th. I'll raise 0.93 to the power of 4. And that gives me 50 million times 0.748, etc. So multiply that by 50 million. And I will still have, or rather my little brother, will still have 3740260.5, so I'll round it up. So 37 million bacteria will still be in his ear at the end of 1 day. 5 days, well, first we need to figure out how many hours that is, so we'll multiply 24 times 5. Or actually, we don't need to go that route. We know that 1 day, t is 4, so 5 days, t is 4 times 5, so that's 20. So I'll set this up. So I have 50 million again, times 1 minus 0.07 to the 20th. Well, I know that 1 minus 0.07 is 0.93. So I need to raise 0.93 to the power of 20. And that's going to give me 0.2342, and then it continues. So I multiply that decimal by 50 million. And at the end of 5 days, there's still going to be 11,711,943.7. So we'll raise that to 44 because, again, we don't have parts of bacteria. So at the end of 5 days, there's still going to be 11 million bacteria in your brother's ear. 1 week is 7 days. So I do 7 times 4, and that gives me t is 28. So we'll set this up again. We already know it's going to be 0.93 to the 28th. So I will do that calculation first. And that gives me 50 million times 0.13107, and that continues. Multiply that by 50 million. And at the end of a week, we're down to 6,553,790.6, so we'll raise that to 1. So we're down to 6 million bacteria. If we had only gone 3 hours, that's half of t. So t would be 0.5 for 1/2. If I raise 0.93 to the power of 0.5, I'm going to get 0.96. So let me just write in my 50 million. Times 0.9643, etc. And I did round that to the nearest whole number, so there would have still been 48 million bacteria at the end of 3 hours. Now we could find out how many days it would take to kill all of the bacteria. We want y to equal 0. So we would set 0 is equal to 50 million times 0.93 to the x, and we would have to solve for x. At this point, we don't actually have the mathematical function to do that, but it can be done. Okay, and did that represent growth or decay? Well, we were killing bacteria off, so that represented decay. Okay, so another example. Over the last several years, there's been an increase in the amount of school-age children carrying cell phones. current estimates are that there are 1,237,000 students in the United States with cell phones, and the amount of children with phones will triple every 10 years. So we're going to use, because we're tripling, that's multiplying by 3. So we'll use y is equal to abx. Oh, actually, hold on one second. Okay, so we have 1,237,000 students times 3 to the x. Now, we don't know what year this started. It says current estimates. So since it's currently 2014, I'm going to go ahead and say that that was our starting year. Now it's going to triple every 10 years. Now if we're at 1 year, t will equal 1/10. Okay. Actually, you know what? Let us do this. Let us take this back because of this number. We'll take this back to 2010. We'll say that current year is 2010. So instead of equaling 1/2 or 1/10, t will be 1/2 because it's every 10 years. So 1t would be 10 years. Okay. I just don't want to make the fractions too difficult in the example problem. So we'll raise our 3 to the power of 1/2. So that means we'll do 3 to the 0.5 first. So 3 raised to the power of 0.5 gives me 1,237,000 times 1.7321, actually it's 0.5 and then it continues. And multiply that by 1,237,000. And I actually get 2,142,546.8. So I'll raise that to 545 because just like we couldn't have part of a bacteria, we can't have part of a person. So in 2015, if this number was current in 2010, there would be almost double the amount of people with kids with cell phones. Now, if we go to 2100 and we started at 2010, if I take 2100 and I subtract 2010, I have 90 years. If I divide that by 10, that gives me t is equal to 9. So in this instance, I'll raise 3 to the 9th. So I'll have 1,237,000 times 19683. I'll multiply that by 1,237,000. And according to this, in the year 2100, it's actually 2.4 times 10 to the 10th. So I'm going to actually write this out. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. According to this growth figure, 24 billion kids will have cell phones in the year 2100. Now, considering that there are not even 20 billion people on the planet, this seems very unlikely. There currently, I want to say 6 to 8 billion people on the planet. I don't know the exact figures off the top of my head, but certainly not 24 billion people on the planet. And even if there were exactly 24 billion people on the planet, they would not all be kids. So if exponential growth does not have a cap, it can continue on forever. But the reality is that when you talk about population, as population is increasing from new people being born, it is decreasing from people dying, and you hit a cap. Population cannot go above what the land will support. but we're not calculating for that. So we'll just go ahead and say there are 24 billion kids in the year 2100 that will have cell phones.